What's going on, everybody? Welcome back to another lecture video. This is the last lecture for this chapter of inner product spaces. Wow, 3 lectures. Not to mention, the next chapter will be, if I'm not mistaken, our last chapter of linear algebra. So we're almost done. And the next chapter will focus on eigenvalues and eigenvectors, which it should be relatively short, question mark? Perhaps. But before we get into that, we gotta finish this one, and this is about orthonormal basis and the Grad-Schmidt process. So let's get started with this one. So before we actually talk about the Grad-Schmidt process and the orthonormal basis, we're going to do a little bit of vector space review. So back in the chapter with vector spaces and subspaces, oh, lovely chapter, we learned that a vector space can have multiple bases and some are more convenient than others. For example, we have the standard basis for like a standard basis of a regular plane, which is B1, 0 and 0, 1. And that's the most common bases that we know when it comes to different dimensions. So what's so special about like bases? Other than they're able to create all the vectors in the vector space, another thing is that they are mutually orthogonal. So what that means is that their dot product, if you take the dot product amongst each other, they should be equal to 0. So they will be perpendicular from each other. And so each vector in a basis is a unit vector. That's some of them, not all of them. Some vector spaces or some vectors in the basis is a unit vectors, others are not. But for this case, in terms of the standard bases, they are mutually orthogonal, and the vectors in the bases is a unit vector. And so why do these characteristics matter? Well, they can help us develop a procedure to constructing such bases that are not only mutually orthogonal to each other, but also have a unit vector in each vector, or in the set. So have a magnitude of 1. And this is what will be known as the Grad-Schmidt orthonormalization process, which we will get to later. Before we start talking about that, I've been throwing around like the word orthogonal and orthonormal. Well, we already know what orthogonal vectors are, but what about orthonormal? So, given a set of vectors in the inner product space V, we're gonna use this given to define what an orthogonal and an orthonormal set is. So if every pair of vectors in S has an inner product equal to 0, then they're orthogonal, which makes sense because we discussed it like a couple chapters or lectures ago, that orthogonality means that two vectors are 90 degrees from each other, so they're perfectly perpendicular. Now, if the set or if each vector in the set is a unit vector, then S is orthonormal. So if the bases or the set, if each vector in it has a magnitude of 1, i.e. a unit vector, then that means that set is also is what is called orthonormal. So if a basis, or if S is a basis, then it is called an orthogonal basis or an orthonormal basis respectively. So yeah, that's kind of like putting two words together, and it'll mean like it's like literal sense. So if you take an orthogonal set, and then we realize that the set is also a basis, then that means it is an orthogonal basis. And then same thing goes, if the set is orthonormal and the set is also basis, then that means it is called an orthonormal basis. I guess if some people don't really like using words, I wouldn't say pictures, but I guess more of a like mathematical visualization. So if we are given the set S that contains V1, V2, and Vn, then it is orthogonal if their inner product of Vi and Vj is equal to 0, where I and j are not equal to each other. And it will be orthonormal if the inner product of Vi and Vj is equal to 0, where I is not equal to j, and the magnitude of Vi is equal to 1 for all i's n, or for all i's from 1 to n. So this helps us create some theorems, because you know that's how math is. You start with a couple axioms and then you can create theorems and just kind of explore everything else. Kind of cool. But yeah, this will help us create some theorems. And so one of them is, if S is an orthogonal set of non-zero vectors in an inner product space V, then S is linearly independent. In other words, if S is a set that contains vectors in which they're all mutually orthogonal from each other, then that means they are all linearly independent from each other, which intuitively makes sense, because if they're orthogonal from each other, then that means they're perfectly perpendicular. And so if you would take the case of 1, 0, and 0, 1, they are orthogonal from each other, and they're also linearly independent, because you can't take 1, 0 multiplied by some constant to make it equal to 0, 1. So this will also bring us a corollary statement, and that will be, if V is an inner product space of dimension n, then any orthogonal set of n non-zero vectors is a basis of V. And so what that means is, if you have if V has a dimension of n, then that means if you have an orthogonal set within that space, then that means it will be a basis of V, which again, you can take the same example with 0, 1, and 1, 0. The inner product space is 2, and because 0, 1, and 1, 0 are orthogonal from each other, it's a pair, which also has a dimension of 2, and it makes it a basis for V. Now, if B is an orthonormal basis for an inner product space V, then the coordinate representation of vector W with respect to V, B as in boy, is W is equal to the inner product of W to V1 multiplied by V1 plus W, or the inner product of W and V2 multiplied by V2, all the way to the inner product of W times V of n multiplied by V of n. And this pretty much is similar to the change of bases chapter. So we will do a couple of examples of these, and probably provide a visual representation if I can make one. I think I can, but we'll see. But for sure there will be an example on this. So now that we've gone through the theorems, and also, like, quick note, the second theorem might be useful for the Gram-Schmidt orthonormalization process, perhaps, who knows, hint hint. But now that we're done with these new theorems that we've kind of created, but we just kind of have to take it as a given, we can now start the Gram-Schmidt orthonormalization process, or the Gram-Schmidt process if you don't want to say it. Knowing one of the advantages of orthonormal bases, i.e. the coordinate representation from like the last theorem, we will now look at the procedure for finding such bases. So the steps to do this, it is 3 simple steps. Oh, 3 is a small number, so it should be simple. Well, the first step is to begin with a basis for the inner product space. Oh, and I will mention that I will give kind of like a mathematical representation in the next slide. So if this is kind of confusing, I suggest pause and ponder for a bit. But if you still don't understand it, just kind of move on to the next slide, as it'll hopefully give you a mathematical representation on doing this. So yeah, you begin with the bases of an inner product space. They don't have to be orthogonal nor consist of unit vectors, because what we're going to do is we're going to find vectors that are going to be orthogonal, and then we're going to convert them into unit vectors. And so the next step would be to convert the given bases into orthogonal base. And then from there, we're going to normalize each vector in the orthogonal bases to form a orthonormal basis. And so I'm just going to reiterate these steps, but like in a more mathematical representation. So we are going to let B equal to V1, V2, all the way to Vn, and have that be a basis of inner product space V. Again, these are not necessarily orthogonal from each other, nor none of them are necessarily a unit vector. And so now we're going to let B prime be W1, W2, all the way to Wn, where Wi is given by, well, W1 is going to be equal to V of 1, and then W2 is equal to V of 2 minus the inner product of V2 W1 over the inner product of W1, or the magnitude of W1, and I multiply that by W1. And then W3 will pretty much be like a similar process. It's going to be V3 minus the inner product of V3 W1 over the magnitude of W1. Multiply all that by the vector W1 minus the inner product of V3 W2 divided by the magnitude of W2 multiplied by the vector W2. And so what this process, it's a very long, tedious process if you have more elements. So like 5, 6, 7, like I feel like 3 is already enough. But what each part represents. So for the first one, well, when you do all of this, it will make B prime an orthogonal basis for V. But what each of these calculations do is, for the first one, we're just gonna let W1 and V1 be the same thing. And then for W2, what we're gonna do is we're gonna take W2 and then we're gonna subtract it by this little algebraic expression of like two inner products divided by each other multiplied by a vector. And what that ends up doing, it makes that vector be orthogonal to W2. So in W2 is going to be V of 2 minus pretty much W1, and this will guarantee that W1 and W2 will be orthogonal from each other. And then from W3 it's going to be the same thing. It's going to make itself orthogonal to W1, which is the second expression that you're subtracting, and then the third expression, the last one, it will make sure that W3 is orthogonal to W2, and this will just go on up until like the n-1 term, and that will guarantee that B prime will become an orthogonal basis. And then after that, you just take the or you just find a unit vector of each new vector of B prime. And so we're just gonna let Ui be equal to Wi over its magnitude, and then set B double prime equal to U1, U2, all the way to Un, and that will give us the orthonormal bases for V. Wow, that's a lot. And so there is an alternative form of the Gram-Schmidt process, and that's pretty much if you just normalize Wi before you use it and to determine the next term, it makes it a little bit simpler, because your next term that you'll find will be not just only orthogonal to the other vectors, but it will already be normalized. If I'm not mistaken, yeah, it should be already normalized. So it just kind of like cuts step 3, in which you just normalize each new vector that you found. But other than that, this is pretty much similar to the the real Gram-Schmidt process. So yeah, that is pretty much it for this lecture. We are going to do a couple of examples on orthogonal and orthonormal bases, and as well as the Gram-Schmidt process, and we'll be wrapping up this chapter of linear algebra. So I'll see you guys in the Blackboard.